Lecture number 4, solar radiation. Uh, what we're talking about now is heat energy from the sun. Right? And all heat energy or radiation emitted from heated objects travels through space as waves in a wide range of wavelengths. Right? There are long wavelengths and then progressively shorter wavelengths. And you measure wavelengths from peak to peak. Now, there's a general rule of thumb about the wavelength in which heat energy is emitted from an object. And this is the rule of thumb. The hotter the object, the shorter the wavelength of heat energy that's going to be transmitted from it. Now, we're talking about the sun and the earth. So let's talk about the temperature of the sun and the temperature of the earth and what kind of wavelength is emitted from each. Right. The average surface temperature of the sun is about 11,000 degrees Fahrenheit, and so definitely a superheated object. And so we refer now to the heat energy transmitted from the sun as short wave radiation. Right, so we're going to be using that term a lot, and we'll be abbreviating it SW. So heat energy from the sun is short wave. So remember S and S, sun and short wave. And so what we've got here is the sun is transmitting its shortwave radiation through space, and then the earth intercepts that heat and gets heated through the day, and usually by late afternoon, 3 or 4 o'clock, we've got our maximum heating of the earth, and then the earth starts to give off its own heat, but it's definitely nowhere near as hot as the sun. Maybe maximum temperature on any one day is 130 degrees, and nowhere near 11,000. And so the earth gives off the heat starting about late afternoon and then continuing all night long as long wave radiation. So from now on, we're going to be talking about the earth when it gives off the heat that it absorbed as long wave radiation, or LW. And sometimes you can actually see the earth giving off its heat in late afternoon. Have you ever been driving on the road, a hot summer day maybe, and looking in the distance on the road, the asphalt, and the asphalt absorbs, the heat much easier than the surrounding environment. And sometimes in the distance you can actually see the heat waves, in the distance. Well, that's actually, you can actually see the long wave radiation starting to be emitted from the earth during the afternoon. All right, I just wanted to show you the electromagnetic spectrum and where the radiation from the sun and the earth plots. All right, we don't have to go into the details, but you can see that the radiation intensity of the sun down there on the left, being is much greater, just being so hot. But it's definitely plotting in the much shorter wavelengths. And then there's the plot of the earth. On any one day, it never gets anywhere near as hot as the sun. And so the earth is going to emit the heat that it gained from the sun as longer wavelengths. All right. So I'm going to do something to you now. We're going to look at 2 diagrams. All right. We're going to look at a daytime picture of incoming shortwave radiation from the sun and what can happen to it. All right. Then we're going to look at another diagram at night, when the earth has, intercepted all the shortwave radiation that it can, and having it give off its long-wave radiation at night. So we're going to have a daytime diagram and a nighttime diagram. And specifically, what we're going to do is look at the effect of clouds on heating, all right, both at day and at night. So let's do the first diagram. All right, this is going to be the daytime diagram. I added the sun here. And so we're looking at our short wave radiation diagram, and we're going to look at the effects of clouds. I want to begin on the left side on a clear day. Now what we're going to do is we're going to imagine 100% or 100 units of incoming shortwave radiation from the sun on a clear day. Right? And we got a clear day. Now, on any one day, kind of a global average, 20% of that 100 will never strike the Earth. It'll be diffused or scattered back to space, absorbed by dust molecules, and so that'll never be used to heat the earth. But, okay, so it's a clear day, and that's it. And so the remaining 80% of that original 100% winds up reaching the ground. And so that's a lot, of that original. And so on clear days, guess what? It's usually warmer out, all right? Hotter temperatures, and it depends, on the season, how much hotter it's going to be, all right? So now let's look at the right side diagram. We're going to have a cloudy day. And we're still, on a cloudy day, going to wind up losing 20%. All right, out in space, you're still going to have scattering and diffusion. But now closer to the Earth, here we've got the clouds enlarged here, right, really closer to the Earth. And we're going to look at the effect of clouds. Now, clouds are great reflectors of shortwave radiation, all right, incredible reflectors. They can reflect up to, if they're really thick, 60% of the incoming shortwave radiation. Now, if they're thinner, maybe reflect about 30% back. I put an airplane up there because there's so many times I'm traveling, it's a cloudy day, and you take off and you're in the clouds, it's bumpy, and there's mist on the windows. But once you get above the clouds, my God, glaring, bright white light. All right. And that's an indicator of the clouds reflecting that incoming shortwave radiation. And so here I've got a diagram, or a picture, of a really cloudy day, but there's a hole in the cloud. And you could see that glaring bright white light and how much is actually being, reflected, not being used to heat the earth. And so on a cloudy day, you can reflect, up to 60%, in addition to the 20% that's never going to be used. So there is a saying in meteorology, too, about this phenomena that, clouds are such a great reflector. They act like a mirror. Now, a mirror reflects 100% back. Right? Now, clouds don't reflect 100% back, but if they're thick, 60% is pretty decent. And so then what could wind up happening is that the water droplets in the cloud can absorb some of the heat too. But on a cloudy day, depending on how thick the clouds are, you're not going to receive anywhere near as much of the sun's rays than on a clear day. So maybe 10% of that original 100%. Right? That means that you're going to have a much cooler day. Or if the clouds are relatively thin, you'll get about less than half. So again, depending on the season, cloudy days, it's cooler, right? You know that already. Now we just kind of explained why. Let's look at the nighttime picture. Right? So it's called the long wave radiation diagram, and we're going to look at the nighttime picture at night, right? And the Earth has intercepted it's all the shortwave radiation that it's going to get during the day, and then it's going to start radiating its own heat, right, at night. And again, we're going to look at the effects of clouds and temperature. I'm going to start over on the kind of left side when it's a cloudy night. Now, the thing about clouds, right, if you've got a really thick cloud cover in particular, the clouds are going to trap that outgoing long-wave radiation and then absorb it and then re-radiate it back down to Earth. And so what's going to wind up happening is we're going to have a heated lower atmosphere and a warmer overnight conditions. And again, there's another saying in meteorology about clouds. Right? Clouds at night act like a blanket. Kind of like a blanket on your bed. If you really think about it, your temperature, your body temperature is 97, 98 degrees, right? And you're laying in bed and you're giving off long wave radiation. Now, if you don't have a blanket on, all of your long wave radiation is going to escape to the ceiling. And what are you going to feel? You're going to feel cool. Right. And so what if you put a blanket on? You put a blanket on and your long wave radiation is going to be trapped by that blanket. And so, in reality, it's not the blanket that's keeping you warm. It's your body, right? Your body heat, your long wave radiation is being trapped by that blanket. And so you're actually keeping yourself warm. And so, that's what's kind of going on with clouds at night. And you really notice it a lot more during the winter season, which is approaching. Whether we're going to have a freeze or night at night. If it's cloudy, we might not, get down to near freezing. Let's look at the right side of this diagram. Clear overnight conditions. When it's clear, well, you don't have the clouds to trap the outgoing long-wave radiation, and so all of the daytime heat that was absorbed is lost to space. So you have excessive chilling near the ground, and temperatures on a clear night will be much cooler, especially noticeable during the cooler season that's coming up. That ends lecture number 4.